Hello everyone and welcome to Solved, where we help you solve problems. In this video, we will be deriving the velocity profile of a thin fluid film falling down the sides of a vertical pipe. We will be using the continuity equation as well as the Navier-Stokes equation in order to determine this velocity profile. So without further ado, let's start with the problem. A pipe of outer diameter d standing vertically has a viscous liquid overflowing through its top and trickling down its outer wall with a constant film thickness del. At some point down the pipe, a fully developed laminar flow profile is established. Determine the velocity distribution in the film. Let's go ahead and solve that problem. I have here illustrated the problem. So we have here a pipe in which water was initially flowing upwards until it overflows at the top portion of the pipe. Now, the overflowing liquid drips down the sides of the pipe, forming a thin film of fluid. The thin film of fluid is what we are interested here. We want to know its velocity profile. So we have here illustrated that our fluid film contains a free surface with a thickness of del and with velocity u sub z varying across the radial direction. If you noticed, I have placed our coordinate system axis, that is the axial direction z and the radial direction r, and I have decided to represent the center of the pipe as r is equal to 0. If we represent the actual radius of the pipe as capital R, then in terms of position, we can say that at the solid boundary, that is r is equal to capital R. In our magnified version, this is r is equal to capital R. That's the solid boundary. And since we have specified that the thickness of our fluid film is del, then the position of the free surface would be r is equal to capital R plus del. Okay, we will be using that representation all throughout our derivation. Now, here is a list of the assumptions that we are honoring for this derivation. First, and the most important, the flow is laminar. This is important because the theoretical velocity profile can only be derived for laminar flow. For turbulent flow, it is much more difficult to derive the velocity profile because it involves the complex nature of eddies. Okay? The next assumption we have is we have a fully developed flow. That means that the velocity at a certain value of r or at a certain radial position does not vary with the direction of the flow. Our next assumption is that our fluid is incompressible and it is a Newtonian fluid. The main consequence of this assumption is that our density and viscosity are constants at a certain temperature, and both the density and viscosity will not vary as a function of the flow parameters. Next, we have steady state flow. And finally, we have unidirectional flow, or the velocity has only one component, and that is the axial component z. Thus, we are saying that the radial and the rotational components of velocity are both equal to 0. Let's begin our derivation with the continuity equation. I have here listed the continuity equation for a cylindrical coordinate system because that is what our system is. It's a cylinder. Okay? Now, let us cancel some of the terms that we are not going to use. And let us justify why do we cancel those terms. For the first term, the partial derivative of density with respect to time, that is 0 because of our assumption of a steady state flow. Our second term is also 0 because of our assumption of unidirectional flow. That means that the radial component of the velocity is equal to 0. The next term is also 0 because we don't have a rotational component of the velocity. Thus, we are only retaining the final term of the continuity equation, the one pertaining to the axial components of the velocity. Thus, our continuity equation simplifies to the partial derivative of density times uz with respect to z is equal to 0. We are going to use this simplification of the continuity equation in conjunction with the equation of motion. Speaking of, we can now see the direct consequence of the continuity equation in the fourth term of the left-hand side of the equation of motion. That is, in the partial derivative of u sub z with respect to z, this is equal to 0 because of the continuity equation. Okay? Now, let us take a look at the other terms of the equation of motion and let's see what will cancel. The first term will cancel definitely because it's a time derivative and we have assumed steady state. The second term will also cancel because we don't have a radial component of the velocity. The third term will also be equal to 0 because we don't have a rotational component of the velocity. Now let's move to the right-hand side of the equation. For the first term, that is the partial derivative of pressure with respect to z, that is equal to 0, presumably because of the presence of the free surface. That means that the pressure drop of the fluid is negligible compared to the other forces acting on the fluid. The pressure drop is only relevant for flows that are fully enclosed. That means that you don't have a free surface. So remember that whenever you have a free surface, you can neglect the variation in pressure with respect to position. Okay? The next term we shall retain because this pertains to the variation of the shear stress acting on the z direction varying on the r direction. So that stays because that is the main source of shear stress in our system. The next term is 0 because our shear stress does not vary on the rotational direction. It only varies on the radial direction. Okay? And that's also true for the next term. This is also 0 because our shear stress is not varying on the z direction. This is a direct consequence of the assumption of fully developed flow. That is, the shear stress at a particular radial position is constant along all of the axial direction as long as the flow is fully developed. Okay? Now, the final term here, rho times gz, we need to maintain this because remember that gravity is acting upon the fluid. Gravity is actually the force that lets the fluid flow down. And the only resisting force here is the shear force acted upon by the solid boundary. So we have two remaining terms in our equation of motion. The first term here refers to the opposing forces that prevents the liquid from falling down. This is our frictional term. Friction is introduced by the shear stress acted upon by the solid boundary to the fluid. And our second term here is the force that allows the fluid to go down. That is the pull of gravity. So what you are seeing here is simply a balance on the forces acting on the fluid. One allows the fluid to go down and the other opposes the movement of the fluid. Okay? That is our simplified equation of motion, and this is what we are going to use to derive both the shear stress profile and the velocity profile. I have here isolated our remaining terms of the equation of motion. So what we have to do at this point is to rearrange this equation such that it will become integrable, and then we will stop once we have the shear stress profile for tau rz. Let's begin. Let us transpose one of the terms to the other side of the equation, and then let us cross multiply so that 1 over r will be distributed. We will have the partial with respect to r of r tau rz is equal to rho g r. Now you have noticed that the gz was dropped to simply mean g. That's because g sub z is the only component of gravity that is acting in this case. It's the downward pull of gravity. Okay? Now this expression is now integrable. If we integrate this with respect to r, this becomes r tau rz is equal to rho g times r squared over 2 plus the integration constants c1. Now, for this to become a specific solution, we have to specify boundary conditions and solve for the value of C1 before declaring this to be the final shear stress profile. Now, for our first boundary condition, we need to take a look at the condition at the free surface of the flow. At the free surface, remember that is at the position r is equal to capital R plus del. This is the surface of the fluid that is the farthest away from the solid boundary. That is the wall of the pipe. Okay? At this free surface, always remember that the shear stress is equal to 0. There is no shear stress happening at the free surface of the flow. That is when we assume that the atmosphere or the air surrounding the film of the fluid does not exert a significant amount of shearing stress into our liquid. Under this set of boundary conditions, once we substitute them to our general solution, it would look like this. Our left-hand side would be equal to 0 because our tau rz is equal to 0. That would be equal to rho g times r plus del squared over 2 plus c1. Therefore, we now have a value of c1 that is negative 1/2 rho g r plus del quantity squared. This value of C1 has to be substituted to our general solution in order to come up with the specific solution. Okay? And that would give us the final shear stress profile. Substituting to our previous equation, we now have R tau RZ is equal to 1/2 rho g r squared minus 1 half rho g capital R plus del squared. You have to always remember the difference between capital R and small r in this case. Small r denotes the radial position. So small r is a variable while capital R gives us the actual radius of the pipe. Okay? So capital R is a constant while small r is a variable. That is important when we are considering integration because small r is integrable while capital R is just a constant. Okay? The final form of our shear stress profile can be simplified now that it will be tau Rz is equal to, divide both sides by small r, we will have 1 half rho g multiplied by the factor r minus capital R plus del squared over small r. This is now our shear stress profile. Now, using this derived equation of the shear stress profile, we can actually prove that at the free surface, the shear stress is zero. If you go back to our boundary condition, at r is equal to r plus del, supposedly, the shear stress must be equal to zero. If you take a look at our shear stress profile, if you substitute r plus del into this term here, this would become r plus del, and then this small r also becomes r plus del, and r plus del minus r plus del is equal to 0. Thus, the shear stress is equal to 0. Okay? By the same token, we can also say that the maximum shear stress occurs at the immediate boundary of the pipe wall. That is, at r is equal to r, our tau Rz becomes the maximum shear stress, TRZ max. And the value of that can be derived from this equation of the shear stress profile. That is simply tau Rz maximum is equal to 1 half rho g times quantity capital R minus capital R plus del squared over capital R. This is our expression for the maximum shear stress. Okay, this is at the wall of the pipe. Okay, now let's proceed. Remember that we are not yet done because this is just the shear stress profile and we are interested in the velocity profile. Now for that, we are going to use our shear stress profile, but we have to reconcile this with Newton's law of viscosity in the cylindrical coordinate system. For Newton's law of viscosity, we write that as tau Rz is equal to negative mu multiplied by duz over dr. This represents the variation of the axial velocity with respect to radial position r. If we combine those two equations, we will have negative mu duz over dr is equal to 1 half rho g quantity r minus r plus del squared over small r. Notice that this equation is already integrable with respect to small r. Let's perform a little rearranging. We have duz over dr is equal to negative rho g over 2 mu times r minus quantity capital R plus del squared over small r. Integrating, this becomes u sub z, or our axial velocity profile, is equal to negative rho g over 2 mu. This is just a collection of the constants multiplied by r squared over 2 minus r plus del quantity squared ln of r plus our integration constants C2. Now, just like what we did with our shear stress profile, let us provide boundary conditions so that we can solve for the value of C2. We have our boundary condition 2, and then let us use our no-slip boundary condition. Under the no-slip boundary condition, we say that at the wall of the pipe, the velocity is 0. We represent the wall of the pipe as small r is equal to capital R. This is the radial position is equal to the actual radius of the pipe. And at this position, we say that the axial velocity uz is equal to 0. Now let's substitute these parameters into our general solution. We will have 0 is equal to negative rho g over 2 mu multiplied by capital R squared over 2 minus capital R plus del squared ln of capital R plus C2. Simplifying this, we simply transpose one of the terms to the other side. Therefore, we will have C2 is equal to positive rho g over 2 mu quantity, etc. Okay? Substituting C2 into our velocity profile, we will now have U sub z is equal to rho g over 2 mu multiplied by the quantity capital R squared minus small r squared all over 2 plus capital R over del squared multiplied by ln of small r over big R. This is now our final velocity profile. We can now say that we have described the velocity distribution of a thin film of fluid flowing down the sides of a vertical pipe. Now, to use this equation, you simply have to substitute a value for the radial position small r, and you can get the value of the velocity. That is, of course, if you have values of the actual pipe radius capital R, the thickness of the fluid film del, and the physical properties of the fluid, that is density and viscosity. Let us verify if we have the correct velocity profile. One way on how we can verify this if we substitute back the boundary condition and if it will return the proper values. Let's substitute back the boundary condition number 2. We say that if we substitute small r with capital R, we should get the velocity equal to 0. That is our no-slip boundary condition. As you see in our equation, once you substitute small r with capital R, this term becomes 0, and the ratio small r over capital R will be equal to 1, and the natural logarithm of 1 is equal to 0. Therefore, if small r is equal to capital R, U sub z is equal to 0, which validates our boundary condition. Okay, one last thing. Let us try to solve for the maximum velocity of the flow. Whenever you have a free surface involved and that the solid boundary is not moving or is stationary, the maximum velocity of the fluid will always exist at the free surface. So let us solve for the velocity at the free surface. Remember that your position at the free surface is equal to capital R plus del, and at that point, your UZ would become your UZ maximum. Let's substitute R plus del into our velocity profile. We would have UZ maximum is equal to rho g over 2 mu multiplied by the quantity capital R squared minus capital R plus del squared all over 2 plus capital R plus del squared ln of R plus del over capital R. This is now our maximum velocity expression for the flow. This exists at the free surface. Of course, we can still apply some simplifications to this equation, but I am just showing you how to determine the maximum velocity of the flow. It always has something to do with the position. Okay, that's it for this video. I hope you have learned something. Thank you for listening, and this has been another problem solved.